Yeah, comes on everyone. Did everyone try this thing? This was the last thing that we did. I gave you this as a homework question. The first one was what? It's a thin hollow shell with a thickness T and a radius R. Instead of the gas as a pressure P. The breaking stress is B. The second thing was a hollow thin cylinder. The first was easy. If you take the FBD of an half shell, others can form. Now see, what are the forces acting on this? So outside is vacuum. So from inside, the pressure is pushing it up. So this force would be pressure into projected area pi r square. Remember, it's not P into 2 pi r square. You cannot add it directly. You have to do the projected area. So pressure into the projected area which is P into pi r square. Now, where is this pressure exactly acting? This force is acting on this thin cross section, isn't it? Are you able to visualize how better? It's imagine a coconut. If you broke a coconut, when you open this, how do you get the shape? The edges will be like this, right? That white part. So all the force is acting on the thin surface here. So the tension is acting on this region here. It's like this. That's your tension. So tension T. Hi, Ishan.
It's acting all over the surface, no?
It's all acting over the entire circumference. It's a cross-section area, the tension.
The force by the pressure is acting on the entire shell.
This is the tension record.
Okay, चलो सही. हाँ सर ठीक है
The
सर.
tension will act only on that cross-section, right?
Yeah.
Pressure will act on the entire surface area. Clear with this, everyone? So once you got the tension, what is stress? Stress is tension by area. Which area? Area of, again, the thin section, isn't it? Tension by, the area where the tension is acting. That would be P into pi r square by 2 pi r into thickness T. Is everyone getting what is this force acting on this thin cross section? So when I take this full shell, the force will act only on, see, this entire thing is hollow, isn't it? There is no material here. The only material is present is on this section. So that is the only place where you can have tension. Whereas the pressure will act on that entire surface area. So this guy would be, so this should be equal to the breaking stress. So B is equal to PR by 2T. There, that's your answer. So pressure should be 2BT by PR. Clear? You should not take pi r square, getting it? Because there is no material there. The tension is acting only on the thin cross section of the edge of the strip. Easy? What about the cylinder? How did you do this? We have a long cylinder with pressure P and thickness T and radius R. Is this clear, everyone? Remember this question, huh? In electrostatics, again, we're going to do this. The cylinder take like this. Take a thin element. If you take an element like this, theta, now we are taking a cross section somewhat like this. If you look at the tension is acting on this entire section here, T. This is the tension acting here. If I try to show you the side view, let me. So we have a cross section like this. Are you able to visualize how it is now? So if this was a cylinder, right, just imagine opening like this. So you'll find the entire pressure will be acting, so tension will act on this surface there. You're getting how it is opening up. So we are talking about this area here where the tension is acting, where the length is L, agreed, and this thickness is T. And this tension is acting perpendicular to this surface here. Able to visualize how is the structure? So here, if you take this cross section here for small angles, so if you just see the side view, you will observe there is a tension, and the force here will be pressure into this area. So we're talking about this entire cross section here, which is pressure into that entire length will be L into R d theta or R theta. Pressure into L into R theta. This is that shaded area. This is P into L into R theta. Theta is very small. So we can take it almost like a rectangle. Or let me do one thing. Let me take it as a d theta. Then you know the technique which we have done. This would be d theta by 2. This would be d theta by 2. So 2t sine d theta by 2 is pressure P into L into R into d theta. For small angle, sine theta becomes theta. P into L R d theta d theta d theta. So tension is pressure L R. So stress will be this tension by area, which is L into T, which is P L R by LT. So bulk modulus will be P R by T. That's your answer.
सर कुछ नहीं समझा
Great. What happened?
सर कुछ नहीं समझा how did you take a small cross section area वो the yellow part
Why can't you take a small part? Did you guys try even the question? Didn't you guys try at all? Just came to the class without trying, everyone.
so I tried the sphere one वो नहीं हुआ so I didn't try this one
This is how you take a small element. Why can't you take a small element like this?
and then what you did so you wrote the stress on this thing how
My diagrams are bad. Then what did you do on this thing? On this entire thing here, there's a pressure into area.
mm-hmm.
Yeah. Then what?
and then there's tension on that area
And then the tension will act tangentially like this.
okay
God, you guys all forgot, huh? ये question कैसा किया था? Where is that? This question, how did you take elements here? Take a small arc, we took this tension 2t sine d theta by 2 is equal to dm omega square r.
mm.
This is like this rotating string, that rotating, what do you call that? We did this even in surface tension, right? Same concept. This one. The only difference is instead of the force acting on a small arc, now it is, acting on that full section there. It's a cylinder rotating now. You're not able to visualize the diagram still. See, it is like this.
So do I see a video for this?
This. There's no video for this. You guys have to visualize everything. There will not be video. Exam में कौन देखेगा video? I gave you guys 3 days to try and didn't try this thing. This is how the cylinder looks.
Mm-hmm.
You're getting it. What we are doing is when I cut open this is the cross section we are talking about. You're taking a small element like this. So this entire force is acting on this section here. So how will the tension act on this thing? Tension will be acting tangentially, right? If I take a small thing here, I don't know, you can't see, I guess. If you take a small section like this is how the element would look.
Okay, I get it.
You're getting this thing, and that arc length will be RD theta here. I thought the diagram is clear, right? No? This is one of my best diagrams. You couldn't understand this.
I didn't get the concept actually.
There's no concept there because there's a pressure inside. How is the tension acting on this? The cylinder is being pushed in every direction, isn't it? If you look at the side view, the pressure is pushing in every direction, God. Because of that, there's a tension developed tangentially into the cylinder. That tension by the area should be the stress. So if you cut that small piece now, this is how the element looks like. Is this getting everyone? So the pressure is acting on this section here. That would be P naught into area. Which area? That shaded area. And how is the tension acting? Tension is acting like this. So this tension ka components d theta by 2 and this component is d theta by 2. Those are balancing the 2t sine d theta by 2. This we did, how many times we did this thing, right? Why are you not clear about this part? This concept is not clear. 2t sine d theta by 2 is Pa.
No, this is clear. This is clear.
So what is P into A? A is the area of that section. What is that section there? You're taking this angle as d theta. So this length is how much? R d theta. And this length is L of the cylinder. So what is that area? LR d theta. और क्या चाहिए तुझे?
So I got it now.
And then what is stress? Tension acting by area. It is acting on which area? It is acting on this side area. Clear?
Yes, sir, clear.
Cylinder is a good one. Remember these people how to do. Maybe this is a better diagram, I guess. Anyone else has a confusion on this?
I don't get why the sphere doesn't develop tension the same way the cylinder does.
It does. Take now. Cylinder, you want to do that, but cylinder where there's no length, right? In a sphere, how will you choose a length here? Tell me. In a sphere, it is more easy to do, right? You can take a full hemisphere. Or you want to take this thing, I can do that also for you. See, for a cylinder, I'll take half cylinder. Okay. Now, what will be the pressure? Now, this entire tension will act on this surface. Tension will act on this surface. And what will be the projected area? P into L into R. Agreed?
Yeah.
So 2 times tension, which is T and T, is equal to PLR. So tension is equal to PL2R actually. Okay, now you'll get the same tension. You can do the same way for cylinder also. Got this? You can take projected area for this also and finish it off. But that reason, if something else changes in the problem, it won't be able to click. This is another way to do this thing, right? If you take an half cylinder, I always have this problem of drawing this half cylinder. It is like this. You're getting for this half cylinder, this is the projected area there. So the tension is acting on this surface here, like this. So that is T, this is T, and the pressure is acting here. This would be pressure into length into 2r. What is the projected area? This entire thing is the projected area. So from here you can say 2 times tension is equal to 2 PLR. So tension is PLR. Clear? You wanted the projected area, that's what you can do here also. But learn how to figure out these elements here. This is important. Because tomorrow what they will say, they will say there's no gas inside, the cylinder is rotating with omega. Or they will say there is a cylinder and someone kept a positive charge on top of it. Due to the electrostatic repulsion, the cylinder explodes. So when you create all that kind of stuff, you should have an idea how to choose an element. But anyone still confused, please ask me. Are you able to get this cross section of this thing? How is that thing? That cylinder, I just made a small hole there like this. You got a gap like this. So the entire tension is acting on this surface. Clear? Ishan, sure, na? Clear?
Yes, sir, sure, got it.
Neil, Vartika, clear with this? Arjun? Aditya? Swastika? Clear? Yasha, got this? Perfect. Next thing. Someone still confused, please ask me. I will try to improve my diagrams. I have to take arts classes now. A 3D diagram, I can't draw better than this. But it's a good one, right? It's a good one. To remember that technique. I remember I told you this 2t sine d theta t by 2 will come out with 6 chapters. Next thing, stress strain curve. So if you try to plot stress versus strain graph, before that we had to do something called Searle's apparatus. So this is an experiment called Searle's apparatus. Idea is pretty simple, but you should know the name. They will suddenly say in a Searle's apparatus experiment, blah, blah, blah. You guys will get confused what the hell is happening. So I'll draw a simplified version of this. The idea is this. On one side, you have a weight m. This is a dead weight, meaning the value doesn't change. This is a constant weight. So this is just to keep the string straight. On the other side, you take the wire which you're going to use. So this is the wire which you're going to measure the Young's modulus. I'll just call this thing Searle's apparatus. Let me do this. Basically, this is an experiment to find the Young's modulus of the wire. Especially they'll ask you this question in errors, which we will see later on. Experiment to find Young's modulus. So here what we do, on this side, we have some kind of, where you can keep on changing this mass. This is a variable weight. So if you look at this diagram here, what they do, when you keep on adding weight, so initially we have something here called a spirit bubble. You guys know what's spirit bubble? Seen in the lab? No? It is like this, it's a device where you have a small air bubble in the middle, and this entire thing is filled with spirit. So this is a spirit liquid, which is alcohol basically. This is an air bubble. So the idea is this. If you tilt this, the bubble will keep moving. For example, if you tilt the shape like this, what will happen to the bubble? The bubble will come here. If you tilt it like this, the air bubble will be like this. So if the rod is exactly horizontal, the bubble will be exactly in the center. So this equipment is actually useful to find whether something is horizontal or vertical or tilted. If you see people who are in the construction, right, when they're installing tiles or they're keeping something, they use this actually, whether to see actually the floor is flat or not. So when it is horizontal, the bubble is exactly in the middle. So this is useful to know whether the wire got stretched or not. When it is horizontal, the air bubble is in the middle. Now, what happens as you keep loading the weight? Let me see if I can get a photo for that. Now, if you keep on adding the weight, one sec, where is this? So if you keep on adding the weight, this is what will happen. So at one point, this guy becomes like this, and the air bubble will shift this way. So this is how you know the right side wire got stretched. And then what we do from here, you can see the screw goes here. So we take this equipment and then we rotate this. Then this screw, which is here. So this is rotated. So when you rotate this, can you see? This screw will make it go up and down. This is rotated, which pushes the spirit. Which pushes the spirit level upward till it becomes again horizontal. You're getting it? Meaning this diagram would have become like this. Then you will keep on rotating this till it becomes again horizontal. So from here, we can measure the elongation, isn't it? So let's say if you move it by certain divisions, here you have a scale here. From there, we can measure. So this gives us the elongation. Because initially it was horizontal. By whatever amount it must have gone down. So this must be your delta L when you push it up. So this gives us the elongation delta L. Then you're done. So what is Young's modulus ka formula? Tension, which I know is small mg, length L, which I can measure, area of cross section. At that time, we measure the screw gauge, and this is delta L. Tension will be small mg, and you know all the values that substitute and you'll get the answer. So the experiment is straightforward. Have a look at this. Where is this? So exam, you know how they'll ask this question? They will give you something like a screw gauge reading. I'll teach you later on 1 calipers and screw gauge again. So the question would be like this: the screw gauge is measured with the radius of the wire is measured with a screw gauge. These are the readings. They would give you something like this sort. I'll not do it right now, but they will show you like this. They will say when a wire is placed between this is the reading. They'll just show you the diagrams like this. So they expect you to figure out the radius from this reading, how to read the screw gauge. And then they will say when the screw is rotated to keep the spirit bubble horizontal, let's say this is the reading. I'm just giving some random examples, like with the vernier calipers. So the delta L is measured with the vernier calipers, radius of the wire is measured with the screw gauge. So this gives you the delta L, and this gives you the radius of the wire. And then they'll ask you find the error in the measurement of Young's modulus. The question will be pretty neat, but we will do when I teach you again errors in the end. But that way, so Searle's apparatus, as such, there is nothing in the question, but you should know the concept, because when you hear the word Searle's apparatus, you should know what the hell they're talking about. Is the experiment clear? So basically, the right side you are loading there. No, they won't give both vernier and screw gauge reading. They'll just give you the diagrams. You have to get the readings. I showed you, no? They will say this is how the reading looks. So they expect you to measure that value. Now, if you take this right hand side and you keep on loading, you'll observe if you try to plot a stress versus strain graph, this is how it looks. This is a theoretical thing. So when you plot the graph stress versus strain, simply think of it like, stress is force by area, strain is elongation per unit length. You're indirectly drawing fx graph basically. So initially the graph is straight line. So if you look at the points here, this is point A, this is point E. I have to make it more curve. This is E, this is U, and this is B. Now let's see what each thing means. So initially when the wire is stretched, so as you keep putting more and more load, the stress will increase. We observe in region OA, stress is proportional to strain, meaning this is what we studied. Meaning the wire will act like a spring. It's a linear function. The more strain you have, more stress you have, more strain you get. So Hooke's law is valid. So all the things that we studied is in this region actually. But right, if you stretch the spring too much, sometimes it doesn't come back. So this point A here is called proportional limit. Because up to this point, the stress is proportional to strain. E here is called elastic limit. We'll talk about that. U is the ultimate strength. B is the breaking limit. And here, if you take this angle to be theta, we can clearly see tan theta is the slope stress by strain. This is the Young's modulus, which is nothing but the slope of line AA. That is the first point. So in O to A, the slope is the Young's modulus. The forces will increase linear like this. So in this region, forces are linear, meaning they will change as a function of elongation, and conservative, meaning there are no losses of energy. This will be a good theoretical question. Up to what region the forces are linear? Up to what region forces are conservative? Conservative meaning the energy can be conserved. Now, if you keep pushing it further, if you keep putting more and more weight, now you will go beyond a region. If stretched further, stress is not proportional to strain anymore. It doesn't act like a normal string. So there's always a limit. You stretch too much and any metal would eventually break down. So Hooke's law is not valid anymore. But the forces are elastic in nature, meaning they're still conservative. Forces are conservative. Right? And up to V, so when you're pulling this up to this point E, if you remove the forces at any point of time, if external forces are removed, it will come back to the natural length. So there is no permanent deformation. There's no damage to the wire. It is not linear anymore, but there is no damage also. It comes back to natural length. So exam, what they'll ask you? Up to what region the forces are conservative? Up to E. Up to what region forces are linear? Only up to A. So forces are conservative in OAE. Meaning here, if you apply 10 newtons, it stretches by 1 centimeter. If you apply 20 newtons, you'll stretch by 2 centimeter. But once you cross A, if you apply 40 newtons, you'll get only 3.5 centimeters. It won't be linear anymore. Have a look at this page. This is up to E. Once you cross E, things will start going bad.
मतलब path independent, right?
Conservative meaning non-dissipative forces, right? Basically, which are path independent.
Yeah.
Clear? Then, so once you cross this point, once you exceed E, the material is permanently deformed. If you stretch further, so in that region EU, so if you go beyond E and if you remove the force, the wire does not come back to the initial position. And it is permanently deformed. So that is what we wrote as OO dash. When you remove the force here, instead of coming back in the red line, it will come back in some other direction. But eventually you will be at O dash. So there's a permanent deformation. So this also has an advantage. So the longer the EU, the more easy it is to make wire. So this length EU is proportional to ductility. That is, higher the EU, more easy to make wires. Now, once you go beyond this, so example, think of like this. Let's say this is material 1. This is your material 2. So they can ask you like this, which material is useful to make wires, which material is useful to make springs? If you look at the red line, the red ka EU is much longer compared to the blue. So material 2 is good to make thin wires. So think of like this, EU tells you how much you can stretch up to the maximum strength. Once you cross U, you'll start breaking down. So material 2 is good for making wires because EU is more. You will stretch much farther before breaking down. Whereas for a spring, you want the spring constant to be bigger. So whoever has a slope more, they'll have a stronger spring constant. If you remember K, which is spring constant, this is nothing but Young's modulus A by L. So more the slope, more the spring constant. So the blue wire, the material 1 will have a higher spring constant. Clear? So if you take a material like glass, you know, how will a glass look like? This is A, this is E, this is U, and immediately it breaks down. Glass won't stretch only. The moment you try to stretch a glass, it will crack. So the glass will have a very small EU. It's very brittle. Whereas copper will have a long EU. It can be into with thin wires. Clear? Yeah, that is melted glass, Nare. Not after it becomes solidified. Now, if you continue further, things will get more messy for the material. In that region U to B, if you observe, something interesting happens here. From U to B, did you observe? The stress is decreasing, but the strain is still increasing. Technically, what should happen? If you increase the stress, strain should increase, more elongation. If you decrease the stress, the elongation should decrease. But once you cross this point U, right, the material got stretched so badly, the inside the molecular bonds got messed up. The whole thing starts behaving like a plastic body. So in the region UB, plastic body meaning think of like a solid fluid types, like the material started stretching, it will stretch on its own. It has lost the ability to, resist. We call it plastic nature, if you remember. A plastic body does not have any restoring forces. The material behaves like a plastic body. That is, there are no restoring forces, or they're very negligible. It's like chapati ka dough. If you push your finger, right, meaning it will deform, but it will not come back to the natural length again. That is, even when stresses decrease, even if you decrease the stress, strain will continue to increase. And finally at B it breaks. So basically once you cross, your story is over. So exam, how they'll ask you, and they can give a theoretical question like this. You can a hypothetical graph. So let's say this region is O, A, B, and C. Can you tell me in which region does it act like a plastic body?
AB.
So remember just now what we said plastic body here? Yeah, got an answer, type in the chat box here. Let others also try. You know the answers. So A to B, what is happening here? That is the reason we are looking at. Even when the stress decreases, strain should continue to increase. So AB is the plastic region. It's a hypothetical material. So you would get theoretical questions on this. What are all the theoretical questions? Here. In which region forces are linear? OA. In which region forces are conservative? OE. Right? Which, if EU is more, what will happen? It's more ductile, easy to make wires. The slope will give you the Young's modulus and plastic region. So these are like 4 or 5 theoretical questions they can pop up on this thing. Have a look at this.
So will the Young's modulus actually no, I got it side.
Come again.
No, nothing. I had this.
Clear? That is about the longitudinal stress. Anyone has any doubts on this graph, please ask me. Quite a useful one. Luckily, it is not there in HSC. Next thing. That's about the longitudinal stress and Young's modulus. The next one is shearing stress or rigidity modulus. So what is this rigidity modulus? Consider we have a block like this. And it is fixed on the ground. So area is A and initially there is no force. If there's no force, it is fine, it just be normal. But the moment you apply the force, this guy is going to stretch. If you see here, this entire layers have moved here. So this would be the displacement of the layer delta x. And let's call this distance n. So we define something called shearing stress. Remember, longitudinal stress is what? Tension perpendicular to cross-sectional area. The shearing stress here is the tension or force in this case. This tension parallel to cross-sectional area by the cross-sectional area. Which is F parallel by A. Then we define also something called shearing strain, just like longitudinal stress and longitudinal strain, but here the idea is different. So shearing strain is given by delta x by d, which is relative displacement between the two layers. So in this case, it is a delta x. If you see the upper layer has moved delta x, the bottom layer didn't move only. distance between the two layers. So you can take this angle as theta, and you can also write like tan theta as delta x by L. So this happens, whenever you're trying to move a book or something, like, think of like this. See, for example, if you have this thing, if you try to apply force in this way, can you see what happened? The book layers, how they're moving? There's a lateral displacement. That's your shearing stress. Basically, last time I told you, remember, if you pinch someone, that's a shearing stress. If you're in a tear a paper, that's a shearing stress. Or you want, I can show that graphical image of man hanging with the skin. So we'll not see that. So that is a shearing stress.
What
kind
if you like stretch the bottom with another force then?
That will be even better. I just kept it simple here. We will do. Let's say if you stretch it with another force, this guy, yeah, it kind of still becomes like this. So let's say initially this was the shape here. Then you take the relative displacement. No? Maybe there's a delta x on the top and delta x at the bottom. Clear? Have a look at this. Just give me a minute. So now if you take the ratio of these two, we define something called rigidity modulus. If you see the symbol kind of looks like viscosity. So in case of fluids, we call it actually coefficient of viscosity. For solids, we call it rigidity modulus. If you see the strain ka term kind of looks like, velocity gradient. Shearing stress by shearing strain. So this is the force parallel by area by delta x by L. So higher the rigidity modulus, more difficult to think of like this. A plastic sheet is more difficult to tear compared to, it is easy to stretch. A plastic sheet has less rigidity modulus compared to paper. I wrote reverse. More Rita compared to paper. It's more easy to, tear a paper. It is more difficult to tear a sheet. Whereas a plastic sheet will have less Young's modulus. A plastic sheet is more easy to stretch. A paper won't stretch that easily. It will break before that. Plastic sheet has less Young's modulus compared to paper. So basically think of like this. A sheet is nothing but, whenever you tear a paper, what you're applying is shearing stress. Tearing a paper is shearing stress, whereas, stretching a paper by pulling it is like a rigidity model, Young's modulus. That's a longitudinal stress. So theory-wise, only this much is there. Simple, straightforward on this. Let's see some questions on this. You can note down the thing in the red box. Clear? So we have a block like this. So we have two blocks like this. The upper one, rigidity modulus is eta 1. The low one ka rigidity modulus is eta 2. This is x is equal to 0. This is x is equal to some a. This length is L. This length is 2L. Area is A, and the there are two blocks which are stuck to each other. The ground is fixed. The lower block is fixed to the ground, and here you have stuck both the blocks together. You're getting? So if you look at the side view, it would just look like this. There's a block on top of another block. Then what you did, you applied force on the lower block. Now the lower surface is fixed, it can't move. This is how the whole thing got stretched when you applied force F. So this point will still remain x is equal to 0. This point is x is equal to a. So this upper part reached x is equal to 2a. And this part went to x is equal to 6a. The heights will remain same. So this height is still L. And this height is still 2L. So heights didn't change. This is eta 1 and this is eta 2. So when force is applied, so this is steady state. Eventually the system will reach a steady state. Basically, when you apply the force, this is going to stretch. Find eta 1 by eta 2. Are you able to visualize the diagram? So you kept a block on top of a block. If you pull the upper block, the whole thing will actually stretch. The upper will stretch even more. So this is how the shape became after applying a force. So using this diagram data, you need to figure out what is the ratio of rigidity modulus of the upper part and the lower part. There are two different blocks. Remember, this is the only formula you have. F parallel by area delta x by L. If both were made of same material, what would have happened? If both were made of same material, it would have been like this, isn't it? The whole thing would have been a straight line. Because both are different materials, they will have a different, displacements horizontally. The shape became a little weird.
On the top surface, both the points will have the same displacement, right? On the top, surface.
Which meaning this one you're saying?
Like, yeah. On that, all the points will have same displacement.
Matlab force F is acting like this in the middle, so it's being pulled.
Okay, right.
I didn't show you a 3D thing. You want to see my artistic skills? I can try.
Just that the point on the left should be above A, x equal to A then.
That point won't be there anymore. That's what I'm saying. When you applied force, even this point will move, no? Even this layer with the interface also will go ahead. So this point you're saying, right?
I got it. My
got it,
doubt.
no?
Yeah.
Okay, we have one answer 2:1. Anyone else got that? We have 1:2. Okay, so just be careful. One of you must have goofed up or down. Okay, we have two 1:2s. We have two 2:1s and two 1:2s. Or three 1:2s. Easy one. See, for the lower block, if you take, or for the upper lower block, what is rigidity modulus? Eta 2 is force. Force is F only. The tension is same everywhere. Since it is in steady state and the ground is fixed, at every cross section, the tension is same. Because nothing is moving. Area of cross section is also same. So that doesn't change. Now look at the lower one. The relative displacement, we are talking about the ground and this guy now. What is the displacement? It has gone from 2A, from A to 2A by length is L. Agreed? So this is FL by A into small a. For the upper block, eta 1, it is the same force F by A. One of the displacement is, it has gone from 6A. Initially it used to be at A, now it has gone to 6A by 2L. This is FL by, sorry, this is 2A. This point here used to be at A, now it is at 2A. This point used to be at A, it is at 6A. So what you're interested is this relative displacement. For the second block, we're talking about this is the displacement. You're asking Arjun, what happens if you apply the force at the bottom also?
Yeah.
So if the bottom itself, see, the bottom itself has moved A forward and this guy has gone 6A forward, the difference would have been 4A.
Right.
You take the relative displacement. So we are not interested in the individual displacements, we're interested in the relative displacement. So this guy would be 6A minus 2A by 12. So this would be FL by 4 net 2A. You're done. So eta 1 by eta 2, if you divide them, you get 1:2. Easy? That's it. There's nothing much there. You just need to take the relative displacement of the upper surface and the lower surface.
Sir, the area will be different, right, in the second and first block?
No, it is the same area. Na? Kyun change hoga? It is the same displacement, right? When you push it, this area will
Okay,
still
okay.
remain same.
Okay.
The parallel area, na? All got this? Any doubts on this? Next one.
So
Next one.
basically at the interface also it's fixed, right? Like between the two blocks.
Said na blocks are stuck together at interface.
Acha, right.
They're stuck together with a glue or something, or else they would have gone off, na?
Understood.
Now, let's say we have a cube. Right?
If there's friction between them, will that be equal to the force that you're applying on the?
If you're in steady state, yes.
Okay.
So the ground is smooth. We have a cube of side L. Rigidity modulus is eta. There's no force. When you apply force, the cube actually becomes like this. So when a force is applied, the sides are curved. It won't be a line anymore. Because the bottom is not fixed, it is free to move. So I want you to find equation of this curve. It will be a very slight curve, but it is curved. It's not a straight line. If this had been fixed on the ground, and if you applied a force, it would be a proper parallelogram. Then this would have been a line. Now, because it is smooth at different points, you have different tensions. You can take masses also M. I don't think you need it, but okay. Let's get this. Ever pulled a rice bag? When there's a heavy rice bag in the kitchen or something and you're dragging out, you will notice the upper part will come more closer and the heavier part is still at the back. So you will see the entire structure, that entire thing gets curved up. So you can visualize whenever you're pulling something heavy, or when your sister doesn't want to come and you catch her hands and legs and drag. If you see your shape of your sister also changes. It's based on rigidity modulus. Never done that with your brother or sister? If you have an younger sister or brother, you will know. If you are the younger one, you must have known it. You must have done something and must have gone under the bed, and your sister or brother will come and drag you out. My mom used to do that. I used to do all the nonsense things outside and used to come and run and hide under the bed. My mom used to pull me out of the bed and used to beat me with a wire. My mom ka favorite weapon is a cable wire, double folded. Because sticks never used to work, I used to break them. I became too strong. Let's get this. You guys won't know all these things. It has been a long time since your parents must have beaten you right and left. Ne? No, you still get beatings. And then you're very lucky. How to do this thing? It's a good one. Malika, diagram is clear? Everyone agrees, right? It's going to curve. So that thing is important, the belief, it will curve. Now get the equation. So first of all, when you're applying force F, this will have an acceleration F by M. If you take a small region here, up to height Y, so for this region, the tension is T, mass will be M by L into Y. Acceleration will be the same. So tension will be M by L, Y into A. A is F by M, so Fy by L. So tension is not constant. As you go up, the tension will increase at every intersection, the cross section, right? The tension will increase as you go up. Because obviously, think about it. Here you have to pull only this much mass. If you go here, then you have to pull this much mass. The higher you go, the more mass you have to pull to the right side. Tension will gradually increase. So tension at every section is not same. Now, coming back to the curve here, if you exaggerate the figure a bit and take a small region, let me just take that curve. I'm exaggerating this thing. So at this point here, at a distance height y, if you take a small section here, this is dy. So this region has shifted by small dx. So you're getting how is that? So at a height y, a thickness of dy, it's like acts like a small thin, cuboid. We can assume the tension is constant. So you're taking a small region here like this. You're talking about a small region like this. So whose width is dy and that horizontal displacement is dx. Now applying the formula for rigidity modulus, what is the rigidity modulus? Tension, that is T, which I know. Area, relative displacement, that is dx, by the distance between the two layers is dy. Agreed? So for that small cuboid of thickness dy, this is the relative displacement. This is how the shape would have looked. This is dy and this is dx. Then you're done. So this would be eta a dx tension into dy. Tension is Fy by L, integrate on both sides. So F by L integral y dy is equal to eta a dx integral. This would be fy square by 2l is equal to eta ax. This is a parabola. 2 eta al x by f. It is this horizontal parabola. Have a look at this. Area is L square, right? You can do that. So area is L square. So 2 eta L cube by F into X. Right, Lakshmi. Check others. Idea is easy because the tension is variable. Every section will elongate different amounts. Because of that, the shape is not line anymore. It became a curve. So the higher you go, more tension, more elongation. So the shape has become a parabola. Now the idea is important because this still looks easy, but exam they can do like this. Eta is equal to eta naught y square. Means as you go up, the eta ka value is also changing. And then they can ask you different curves and all, but idea is the same. Once you got this logic here, you just need to substitute eta ka value. You get a new function. Have a look at this. Clear? Next thing, turn in the page. Any doubts on this? Aryan, Saina, clear with this? Rehan, Vartika, Yasha, clear? Ali, got this? Next one. We have a cylinder here. Solid cylinder. Radius r, length L, eta, it is fixed to the ground. Now you're trying to twist the cylinder. Remember torsional pendulum? Initially, this point was O. This was point A. So when you twisted this by an angle theta, the A reached here, and this whole angle got twisted by theta. This whole angle got twisted by theta. You're getting how it is? So it is like after washing clothes, how you take this cloth and try to twist it. That's basically the torsional torque. You're twisting it. Or ever, you caught your sister or brother ka hand and try to twist it. Pinching is actually twisting. That is torsional torque. So all these are there. So the question is, so when you try to twist it by an angle theta, find the torque required to twist it. This is basically called as torsional torque. Then I can ask you this also, find the time period for small oscillations. If it is twisted by a small theta and released, find the time period for oscillations. So torsional torque or twisting torque is applied on the upper surface. Twisting the cylinder by angle theta. Cylinder, upper surface twisting angle theta parallel to the ground. So basically this entire thing got twisted, it's still parallel to the ground, but it got twisted. Find the torque as function of theta. Let's get this. Yeah, that is the result. You have to prove it.
प्रूव करने के बाद ही
Okay.
I did it and then
Chalo, good. Others, try. What if it is a hollow cylinder with inner radius R1 and outer radius R2?
फिर then जो लिमिट्स लगेंगे वो 0 से R की जगह R1 से R2
What if you have it like this? You have a cylinder like this and you have a big cylinder like this. इसका radius R1, इसका radius R2. इसका length L, इसका length L. Now if you twist it, then what is the angle twisted? Others, try this. Finish all this first. How do we do
Torque at the
this?
junction would be the same जब
Same ना, हाँ, यदि steady state तो रहेगा.
हाँ तो इन दोनों के बीच में like we'll take some theta naught and
Try.
then take
करके मुझे फोटो भेजो. The important thing is, how do you choose an element? How do we choose an element? Yeah, it's a ring, basically a thin cylinder. At a distance x, we take a thin ring like this. Now, when you twist it by theta, this whole thing has moved by how much? X theta. So here you are comparing between this point here and this point on the ground. This point has no displacement, but the point exactly on top is moving by x theta. So for the ring, if you apply eta is the tension in that ring by area of the ring by delta x by d. So from here we get the tension in the ring will be eta. Area of the ring is 2 pi x dx. The displacement is x theta, and the distance between the topmost point and the ground is L. This is the tangential tension, okay? This is your tangential tension on the ring. So every cross section will have different tensions. It's not the same. Then the torque on the ring will be the radius x into the tangential tension, which is 2 pi eta theta by L x cube dx. So the total torque on the cylinder or that upper surface will be integrate all the ring torques. We'll go from limit 0 to r. So 2 pi eta theta by L x cube dx 0 to r. So we end up with torque is equal to pi eta r power 4 by 2L into theta. Now for small angles, we can write torque is equal to I alpha, which is pi eta r power 4 by 2L theta. I is nothing but for a cylinder, what is the moment of inertia? Mr square by 2. What happened, Vihan? Ring is what? Actually, it is this full cylinder, actually, it is a thin cylinder, which is getting twisted. So moment of inertia would be m r square by 2 alpha, take a minus sign because it's a restoring torque. And then you get pi eta r power 4 theta by 2. I showed in the next page. This is the main result, right? If you see, this is proportional to r power 4 by L. Thicker the cylinder, more difficult to twist the cylinder. If this had been a hollow cylinder, have a look at the integration. Clear how we did this thing? So take every small ring, and because see, every small ring will have different area, every ring will have a different displacement. What displacement you're talking about? Tangential displacement. From the initial position, how much did each layer has rotated? Each layer has rotated x theta. Now, if you take this had been a hollow thing, let's say if this was a cylinder with a hollow thing like this. If this is R1 and this is R2, then the torque would have been pi eta R2 power 4 minus R1 power 4 theta by 12. That would be the difference. We can write torque is equal to I alpha. This would be, so that basically is the torsional constant. Pi eta R power 4 by 2L theta is I alpha is mr square by 2 alpha. In torsional pendulum, if you go and see, this is called the torsional constant K. This is how it was derived. There I wrote it, I told you we'll prove it here. So from here we get alpha is equal to minus pi eta r square by ml theta. This looks like A is equal to minus omega square x. This is your omega square. So the time period for small oscillations will be pi eta r square. You can play like this. As you go on across, then theta will, theta will be different for different thing. But you're applying torque on the upper surface, no? So we are finding torque on the ring. That is the reason. It has to change, isn't it? Because this is x theta, this is 0, meaning they're all not twisting by the same amount. Is this clear, everyone? You can ask time period from here. You can ask for a hollow thing. Do have a look at the integration once more. So rigidity models really don't have too many variations. Clear? Next thing. Yeah. See now, in the formula delta x by d, what is delta x? Relative displacement between two layers. By distance between the two layers. Here, one of my layer is the upper surface and one layer is the ground. Got it? Clear with this, everyone? It's a good question. Next one. So exam, what they can ask you? For a given volume, which is more stronger, a solid cylinder or a hollow cylinder with a cavity? They can ask a question like that. You tell me what is the answer for that. For a given volume, means the amount of material you have is same. That steel you can use is same. And you're trying to construct a pillar. Is it a good idea to construct a solid iron pillar or a hollow iron pillar where there is a twisting involved? Right? For a given volume, which is bigger? K of solid. Cylinder K is the torsional constant. K of the hollow cylinder with thickness or solid cylinder with cavity, both the same. Think about it. Prove it mathematically and see. Tell me. Next thing. Bulk modulus. I will leave that to you. Find it out. You need to understand, meaning if the material is same, here it is r power 4 minus r1 power 4. So is it a good idea to make something like 0 to 2, or is it a good idea to make something like maybe 1 to 2.3 or something like that. The difference, which will be bigger? So bulk modulus B, this is the third one, the third stress. So bulk modulus is simply higher the bulk modulus, more difficult to compress the body. So if you have a body like this, so this volume stress is as good as pressure. So we define bulk modulus as volume stress by volume strain. The volume stress is nothing but the force parallel by area, which is as good as pressure. Volume strain is delta V by V. Again, be careful. Delta V is the change in volume from natural volume. We have discussed this in the thermal strain once. We will see question based on this. You will get a better idea. So this is the formula there. So bulk modulus is given by minus dP by dV by V. This is the final form of this. What this equation tells is, for a change in pressure delta V, dV is change in volume for an additional pressure delta P. That's why you get a minus sign, because it compresses. We define something called compressibility, which is 1 by bulk modulus. So bulk modulus tells you how difficult to compress. Compressibility tells you how easy to compress. Have a look at this. Take a small break. Come back by 7:15. We'll have a small short break. Don't want a break? I'm fine. Go take a 5 minute break and come back. Any doubt so far? Please ask me. Okay, come back by 7:15. Yeah, let's start. Comes on everyone. Now, if you take an example for this, bulk modulus for isothermal and adiabatic process. You can even bring thermodynamics into this. So for an isothermal process, PV is constant. If you differentiate on both sides, you end up with PdV plus VdP is equal to 0. So if you rearrange the terms, bulk modulus is dP by dV by V, which is P. So bulk modulus is equal to pressure. What is the meaning of this? This tells you higher the pressure, more difficult to compress the gas. The meaning of bulk modulus is it tells you how difficult it is to compress, and we are getting bulk modulus is equal to P. So if a gas at 1 atm and if there's a gas at 10 atm, the 10 atm one is more difficult to compress. So bulk modulus in an isothermal process is the pressure only. Same thing if you do with the adiabatic process. We know in the adiabatic process PV per gamma is constant. If you differentiate this, dP V power gamma plus P gamma V power gamma minus 1 dV. So if you do minus dP by dV by V, you end up with gamma P. So you can clearly see here, it is more difficult to compress a gas adiabatically than isothermally. If you're compressing a gas through an adiabatic process and in an isothermal process, adiabatic is more difficult. Gamma P is always greater than P. It's more difficult to compress the gas adiabatically. Than isothermal. These are the theoretical questions, right? Clear with this? I could have given you any random process. I could have said, PV cube is equal to constant or PV power x is equal to constant. The idea would have been the same. So for a gas, the bulk modulus is depends on the process. Clear? Next one. Let's see a question based on this. So there's only one formula on this. Bulk modulus is minus dP by dV by V. Easy one. We got a lake here. So we have a small ball of radius r. Bulk modulus is B. The depth of the lake is h. The ball is thrown into the liquid. As it sinks, when the ball sinks to the bottom, find the change in radius.
So could you go to the previous page?
What am I defining as a modulus? What is bulk modulus meaning? It tells you how difficult it is to compress a system. That system is the gas itself.
Every material के लिए all this different moduli they are
This is for
constant ना?
gases. Solids के लिए constant होगा.
अच्छा,
ये gas है God.
okay.
Does a solid has isothermal and adiabatic process for a solid?
No.
चलो add कर ले तुम देख ले for gases. Happy? A ball is dropped into a liquid. into a lake of depth h. So find the change in radius of the ball at the bottom of the lake. Delta r when it sinks to the bottom. Assume delta r is very, very small compared to r. So outside the pressure is P naught. So when it goes to the bottom of the lake, the pressure increases, because of which the ball will have a slight compression. So find the change in radius of the ball. Get this easy one. Okay, we have one answer. Again, remember, you're not interested in pressure, you're interested in change in pressure. So here the pressure on the surface is P naught. Pressure here is P naught plus rho g h. So the change in pressure is rho g h. So when you apply the bulk modulus is minus dp dv by v. So minus rho g h by dv by v. Now for the volume of a sphere, v is 4 by 3 pi r cube. dv will be 4 by 3 pi 3 r square dr. So we'll get bulk modulus into dv is 4 pi r square dr. By 4 by 3 pi r cube is minus rho g h. So you end up with dr is equal to minus rho g h by 3b. Minus indicates it decreased. Yeah, expected. The radius of the ball should actually decrease. Have a look at this. Since the dr is very small, you can use differentiation. If it is very big, you can't do this.
I did without differentiation.
What did you take? You took dv as 4 pi r square dr.
No, sir.
Surface area into thickness. What did you do for dv then? You used
I
errors.
Like usual.
What is that usual? Send me the photograph. Clear with this? Easy. Next one. 4 rho g h by r cube. Anika, did you get your mistake? I want dr, na? Everyone clear with this? Saina, clear with this? Maulika, Ali, got this? Neil?
So why can't you just directly write dv as 4 by 3 pi dr cube and then
4 by 3 pi dr cube. What are you talking?
like just the change radius, like the change in volume equal to 4 by
Okay.
3
What?
pi.
Yeah. What?
Change in
4 by
radius.
3 pi?
Change in radius cube.
Oh, that's how it works according to you. So that means if the radius has gone from 1 to 2, the change in volume is 4 by 3 pi 2 minus 1 whole cube.
Oh, sorry.
Or is it 4 by 3 pi 2 cube minus 1 cube? Basically on Earth, na, the spheres behave normally. Maybe on your planet it is different. So please use Earth curve max. Don't use alien spheres. Oh, hota hai actually. That's a very common mistake. Clear with this? Next one. Next one is even better. We have a container filled with liquid.
So in the previous question,
Bolo.
that thing will be dr by r.
dr by you're right. So एक r आएगा extra. You're right. I forgot an r. So we have a liquid here. There is a solid sphere at the bottom of the lake. Radius is r. Bulk modulus is b. And density of the liquid is rho L. Now you took a block and it is thrown into the liquid. And the base area of the container is A. A block is thrown into the liquid. We have two cases. Case 1, density of the block is greater than density of the liquid. So basically it will sink. Case 2, density of the block is less than density of the liquid, it floats. Find the change in radius of the ball. Again, assume delta R is much less than R. So initially everything is fine. So when you dropped the block, something happened because of which the pressure increased. And because of that, the spherical radius changed. There are two cases. The rho B is greater than rho L and less than rho L.
ब्लॉक का वॉल्यूम
ब्लॉक का वॉल्यूम चाहिए क्या? हाँ ले लेना. इट्स अ क्यूब ऑफ साइडल. You will need it. Take it as a cube of Seidel. What is the catch? Why the hell is the pressure changing? There are different ways of thinking. One thing I'll tell you, when you drop the block, the water level will rise, because of which there is an increase in pressure, P naught plus rho g h. That is one way of thinking, but that will be lengthy. Think, I'll give you 2 minutes. Figure it out what's happening. This will be a pretty good advanced question. Huh? It's not tough, but it will be a good one. Block also compress. Block का matter नहीं करेगा. Assume block is rigid. If I have to give that, na, then I have to give block ka bulk modulus also. Rho g L cube R. But Lakshika will both, for both the cases it will be the same answer. Think. I'll give you another 1-2 minutes. We will wrap up this chapter today. Like you saw, right, the number of questions we have in Young's modulus, that is much higher than this rigidity modulus and bulk modulus. You really don't have too many varieties on this. That too, I made one or two non-standard ones. At a mains level, though, they won't ask such things only. It is straight. You don't have any much questions on rigidity modulus. -3 rho GL Q bar by V. Okay. But that rho is what? Rho of the liquid or rho of the block, Adrat?
The row of the sphere.
Rho of the sphere. Sphere क्या कर रहे हैं? Sphere is just sitting there.
A row of the liquid, sir. Row of liquid.
That sphere is just sitting there. It doesn't give a damn about anything. Why are you bringing that into the picture?
Is row of the liquid.
Let's see like this. Let's see on the block. The two cases we have. Case 1, when rho body is greater than rho L. Initially, what is the pressure? If you see the liquid has mg, right? So pressure on the base is nothing but the weight of the liquid mg by area. This is the weight of the liquid. Now, when you throw the ball, then when you throw this block into this, case 1, rho body is greater than rho L, agreed. This thing has sunk inside. Now, if you look at the FBD of the liquid, so on the block, you have buoyancy force upward. On the liquid, the buoyancy force is downward. Do you agree? Buoyant force is down on the liquid. If the liquid is pushing the block up with FB, the buoyant force is pushing the liquid down. Force is down for the liquid. Therefore, the new pressure will be mg. You can take atmosphere also actually. P naught plus mg by A is the pressure at the bottom. Now the new pressure will be atmosphere plus weight of the water, weight plus buoyant force by area. Do you agree? No need to find that height and all that stuff. If you're pushing the liquid is pushing the block with the FB, the block will push the liquid down with FB. And it is the same case. So here, what is the buoyant force? Since it is completely sinking, the buoyant force will be rho liquid L cube into G. In case 2, the block is floating. So it is not completely immersed. This is FB. This is the mass of the block. So the same buoyant force will act on this. So here the pressure will be again the same thing, P naught plus mg plus the buoyant force by area. But here the buoyant force will be weight of the block. It is not completely immersed, which is rho b into L cube into G. It's not completely immersed. You can't take the full volume. Not completely immersed because it is floating. So this itself is a good question. What is the change in pressure at the bottom? You need not find height and all that stuff. You can simply take on the force, the initial force was what? Mg of the liquid. Now you're getting an additional buoyant force. So that is the thing. So in both the cases, the change in pressure is what? Buoyant force by area. That is your change in pressure. So bulk modulus will be minus delta P by dV by V. So this thing dV by V we already calculated. That term comes out to be 3 times dr by r is minus delta P, which is F buoyant force by area into bulk modulus. So buoyant force into radius by 3BA. You can substitute buoyant force here, substitute buoyant force here. You get different answers in both the cases. In the first case, because the body is completely sunk inside, the buoyant force is weight of the liquid displaced. In the second case, the body is partially floating. So buoyant force will be nothing but weight of the block, which is rho b into L cube into G. So in both the cases, you have a different buoyant force. But is everyone getting why the pressure is increasing? Since the block is floating up because of the buoyant force, by Newton's third law, that same force should push the liquid down. So the liquid will feel the total force has become mg plus fb. It's a good way to do it. Please have a look at this. Most people actually try to find the height and all that. You'll get the answer, but it becomes quite complex.
I did the height method only.
This is faster. Or question. Buoyant force concept you're using. Most people forget this. Buoyant force is upward. Buoyant force is upward. That is okay on the block, but on the liquid it is reverse. All clear with this? Any doubts on this? Next one. Aryan, clear with this? Clear, na? Lakshika, Swastika, got this? Utsa, got it?
Yeah.
Next one. We have a hollow sphere. Completely filled with water at 0 degrees. Density of water is 1 gram per cc. Density of ice is 0.9 gram per cc. The bulk modulus of ice is B. Now, if the water freezes to ice at 0 degrees, remember temperature didn't change, so shell won't expand. Find the pressure on the shell. I hope you remember anomalous expansion. When the water becomes ice, it will try to expand. But the shell won't let it expand. This puts immense pressure on the shell actually. In cold countries, now this is a big problem. The pressure is so high, literally the pipes crack. Ishan?
Is the shell rigid?
It doesn't matter, no. देखो temperature change नहीं तो क्यों expand होगा? Okay, you're saying that way? Yeah, assume it is shell doesn't expand. No information is given, no? Remember, if you want to say rigid or not, then I have to give you bulk modulus of the shell. If that is not given, assume it is not expanding.
Okay, sir.
That is what happens. You can see that copper pipe there, how it cracked. So this happens in the cold countries. Let's say daytime temperature is 10 degrees. There is a water in the pipe. Nighttime suddenly temperature drops to -5. The water in the pipes will suddenly expand. The pipes, right, there is no space to go. The pipes will burst. That is the reason in cold countries now, all the plumbing is in the house. If you see in India, we keep the pipes outside the walls. Right? Because when the hell will we get snow or something here? Chance ही नहीं है. Mumbai ka climate to we have only 3 seasons. Summer, hot summer, very hot summer. So we'll never have a problem like this. Let's get this. That used to be the phrase dialogue, in Chennai when I was studying. Chennai has only 3 climates: summer, hot summer, very hot summer. आजकल मुंबई देख के ऐसा ही लग रहा है. This year summer was for 2 days. Summer बोल रहा हूँ. Winter is for 2 days. Let's get this. Let's finish off bulk modulus. Like I said, these are few varieties we have. If you see, there's a single formula. After this, we have a small theory, and we'll be done. V by 10. Right. We have one answer. Anyone else got V by 10? 9B by 10. Which I think is wrong.
No, sir, sorry.
Try easy one, but conceptual. Let's see. Now remember the formula. If you look at the ice, forget about the shell. What will the ice think? The ice, initially this was the water. Let the volume be V. So when this becomes ice, what remains same? The mass. So the mass of water should be equal to mass of ice. So density is 1 gram per cc into volume is 0.9 into volume of ice. The volume of ice is actually 10 V by 9. Now remember, this is your natural volume. If there was no shell, the ice will think I should have been 10 V by 9. You're getting it? That is what the ice will think. But due to the shell, it didn't expand. It is just like that Volca example. Remember that rod?
Natural volume वो कैसे होता है? It never
What is
had
natural
natural
volume? No. If the shell was not there, what would have been? You would have been 10 V by 9, right?
Yeah.
Getting it? But I didn't let you expand, right? So it's like, let's say your shot ka size is M. You eat a lot of food and you become L, but you don't change the shot. What happens? You feel it is tight. Because your natural volume is not that initial volume anymore. Your natural volume has changed. But due to shell, it doesn't expand. Due to shell, its volume is stuck at V only. Therefore, the ice will think it got compressed. You get anything, guys? You should always take the elongation on the natural length, and the natural length changes. So it feels it got compressed. How much? 10 V by 9 minus V. It will think the compression is V by 9. So this is your delta V. Now in the formula, bulk modulus is minus dP by delta V by V. Actually, a V minus 10 V by 9. Final minus initial minus V by 9. So we have dP is minus bulk modulus into delta V by V. The minus bulk modulus, what is change in volume? Minus V by 9. What is volume? V is not V anymore. V is 10 V by 9, isn't it? This is your natural volume. That's what you have to be careful. 9 will cancel. You end up with V by 10. Most people goof up the part. They think the natural volume is V. And the final volume is V. They don't understand why the hell ice is fighting back. Your natural volume is not V anymore. It is 10 V by 9. This is the reason when I wrote this thing, I told you be careful with this part here. This is the reason for writing that whole statement. Natural volume by change in volume from natural volume. The whole reason you're expanding, the anomalous expansion, is because you don't want any internal stresses. Is this clear, everyone? Easy concept, but there's a high chance we will goof up this thing. You'll either goof up at this V ka part, or you'll goof up with this volume ka part somewhere. Matlab, there's a chance. Clear? And normally bulk modulus of ice is around 10 power 9 or something. So that comes to be 10 power 8. That comes to around 1000 atmospheric pressures. It can even break steel pipes. I think ice is 10 power 8, I guess. That's still 100 atmospheric pressures. Copper pipes will literally crack. Clear with this? Easy one, but a good one. Conceptual. Next one. Any doubts on this page? Can I go ahead? Anika, clear, na? Adrit? Next thing is Poisson's ratio. It is just mostly a theory only. The symbol is sigma. So till now, if you see, right, we are saying force is applied, the length is increasing. Great, but we also observe the radius will mess up. So we define something called sigma, which is Poisson's ratio. It is lateral contraction strain by longitudinal elongation strain. Which is minus delta R by delta L by L. Meaning, if you take a rod like this, whose length is L, whose radius is R, and now if you apply force from both the sides, we know the rod is going to expand a bit. But in this process, the radius also shrinks. This thing we have neglected till now. We didn't care about this thing. But this does happen in the things. So length becomes L plus DL, whereas the radius becomes R minus dr. So this ratio of the change in radius का strain, delta, that's what we call lateral contraction strain, delta R by delta L by L. Here the negative indicates if length increases, R should decrease. Yeah, kind of obvious. So theoretically, sigma का value goes from 0.5 to -1. It's a theoretical value. But practically, right, negative values are not acceptable. Because what is the meaning of a negative value? You increase the length, you also increase the radius. It can't happen. So practical value is somewhere around 0.4 to 0.2, in that range it will be there. Getting it? So that is a sigma lies between 0.2 to 0.4. Have a look at this. Questions are straightforward on this. Let me show you one. The questions would be something like this. Example, we have a rod. Length is 1 meter. Radius is, let's say, 2 centimeter. Young's modulus is y is 2 into 10 power 9. Someone is applying a force of 100 Newton and 100 Newton. And they'll give you sigma is equal to 0.25. They'll ask you find the change in radius. The straightforward formula. So we know Young's modulus is equal to tension length by A delta L. So from here we get delta L by L is tension by AY. Tension is nothing but 100 newtons. Area is pi r square and Young's modulus. And what is sigma? Minus delta R by delta L by L. So from that we get delta R is equal to minus sigma R, sigma delta L by L into R. Substitute the values, you get the answer. That's it. Questions will be based on that only. End of the day, they will again depend on the Young's modulus only. So get delta L by L and dump it here. Generally, don't have much more on this in Poisson's ratio. So in this, there are a few theoretical questions though. Let's see that. Clear with this? Now, what do you mean by sigma is 0.5? This they asked in as an exam. Huh? It's like a big sort of mains level question it is. What is sigma 0.5 or something? So they'll ask like this. If volume is constant, I'll write down here, sigma will be 0.5. Let's see how we got this. So volume of a cylinder is pi r square L. Put log on both sides. Log V, log pi, 2 log R plus log L. Differentiate. 0, 0 plus 2 dr by r plus dl by l. So we get dr by r minus by dl by l is half, which is nothing but the Poisson's ratio. So sigma is equal to half indicates the volume is constant. But in real life, what happens whenever you apply force, the volume is never constant. In an ideal case, it is constant. So that is the reason sigma can't be 0.5. But theoretically, yes, it can be. That is the meaning of sigma 0.5. That is the reason you can't have more than 0.5. And the same way, the negative values indicate that L and R both increase or decrease at the same time, which is not possible. That is one. Other than this, we also have, this is again mostly a bits or a CET level question, even main source they can ask. The relation between Young's modulus, rigidity modulus, bulk modulus, and Poisson's ratio. You need to mug up this. 9 by Young's modulus is 1 by bulk modulus plus 3 by rigidity modulus. This is y is equal to 9 beta by same thing, 3 beta plus n. Y is equal to 2 rigidity modulus 1 plus sigma. Y is also equal to 3 bulk modulus 1 minus 2 sigma. There, these are the three relations which you need to mug up. They're in the NCRT, so we don't need a proof or anything for that. This would be mostly a bits or a CET level question. They'll just directly ask you find the relation between them. This is another theoretical question. They'll simply say like this: volume is constant, which of the following is the value of sigma? 0, 0.1, 0.2, 0.5, like that. And we'll keep wondering like, yeah, how the hell did you get a sigma ka value? So this is the proof. So if you see an entire elasticity, right, the main one is the Young's modulus, and then rigidity modulus, we have some decent questions, and bulk modulus also, but really don't have too many varieties on this. Poisson's ratio is just that one thing. There's nothing more. Any doubts on this? Clear with this? Hi,
If we
Shan.
want to prove those relations between y, neta, v, and sigma, how do we do that?
We can prove it, but we don't need it. Oh, delta v by v and all that is there now. If you see here, dekha, sigma is equal to half means volume is constant na. So bulk modulus is what? Delta v by v.
Yeah.
That delta v by v you can write it as what? So in this case here, if you see, this won't be 0 na. This will be dv by v. You can get relations from there and solve.
Okay.
You can prove it, but we don't need the proofs. All clear with this? So that's the last of the chapter. With that, we're done with elasticity. Now I know most of you have this major test coming up this Saturday. So mostly Friday we won't be having a class. Right? So do prepare your exam. Now some of are asking like, sir, abhi 8 major tests are the best thing to prepare is what? See, first thing I'll tell you, major test may, I know it is important. Right? Let's say for example, there's a chapter like waves or something, which we have not done here, and they also finished it somehow. Right? So there is no point in rushing and trying to do that. Some of you are asking, sir, I didn't even understand anything in the chapter. What can I do? If you didn't understand anything in the chapter, then don't do anything.